So I'll give a talk that's based on some work I did with my PhD supervisor, François Michel, with collaboration with Thibaut Taille-Fumier from UT Austin. And so this talk is kind of designed as an introduction to replica mean fields. So it's nice to be so it's the third talk on the subject this week. So hopefully it will be pretty clear. So please interrupt me if there are any questions. So in this talk, I'll talk more about the kind of theoretical motivations, this theoretical reasoning behind replica mean fields, which I'll apply to a simple neuronal model in discrete time, mostly, so as to sort of simplify the talk. So we're interested in neuron population model, so we're interested in the evolution in time of k neurons. K is a number being fixed. And we see it as a network with k nodes that send each other information, and so there are weights on the edges that represent the amount of information sent when interacting. So it could be 0 if the nodes are not connected. We're not assuming that the network is fully connected at all. And of course, because of that, there are correlations in between neurons, and there's a high complexity involved in the dynamics of the systems that prevents mathematical tractability looking at the object itself. So therefore, the natural thing to do is try to simplify the model while preserving some essential characteristics of it. And so in order to make it tractable. And so one question is, what kind of simplifying assumptions should we take? So the classical mean field thermodynamic limit, which is the one that has been used, for instance, I think in all of the talks yesterday afternoon, is to look at the limit when the number of nodes goes to infinity. And they put a scaling on the interactions as 1 over the number of nodes, or 1 over square root of the number of nodes, so as to prevent epilepsy and explosion in the system. But if you do that, one problem is that you lose both the geometry and the correlations due to the finite size of the network. And so what I will present here is the replica mean field, which is a different type of approximation that allows to preserve some characteristics of the geometry of the model and to stay at a finite size even after the mean field limit assumption. So what are replica mean fields? So you take for your network of k interacting neurons, you basically take m copies of it, which we call replicas. And what we do is that we randomize interactions in between replicas. So we're sort of mixing between the interactions between replicas. So if you have an interaction between a node I and a node J, and neuron I and a neuron J in one of the replicas, instead you sort of send this interaction to another replica, to another node to the same corresponding node, but in another replica. And so what we want to do is to show that something interesting happens when the number of replicas goes to infinity, and I'll explain later why it is not kind of natural to think that something interesting will happen. And since we're trying to prove that replicas become independent and that you sort of can look at one replica at the limit, we talk about propagation of chaos in this setting. So here, in order to sort of present the replica mean field in a simple setting, I'll concentrate on discrete time processes. So we're kind of assuming that all the interactions are synchronous, if you want. And we established a class of discrete time processes, which we call fragmentation interaction aggregation processes, or FIAPs for short, which includes, as a particular case, the neuron dynamics of Galvez-Le type in discrete time here. And so here I will present this only in the setting of these Galvez-Le dynamics. And so what are FIAPs? So basically, as I said, it's to simplify the model, it's just discrete time evolution on a discrete state space. And so at each time step, you can know that if you think of it as a neuron, you can spike and be fragile, and your probability that you spike depends on your state. So basically, the higher your state, the greater the probability is. So since we're in discrete time, we assume that activations are kind of synchronous. If fragmentation occurs, then you interact with the other nodes of the network and you send them information. And whether fragmentation occurs or not, you receive the interactions of the other nodes that have fragmented and you aggregate them to your state. So here it's a simple model without replica so far. And then we'll take the replica version of that. So the equations are very simple. So since they are kind of Markovian, we can define them by the one-step transition. So here we'll look just at the equations that give you the state at time 1 given from the initial conditions xi. So xi is the conditions at time 0. The states at time y at time 1 is given by the yi, sorry. And what happens is for each index I, you define a fragmentation threshold probability that depends on state. So sigma I fix I is the probability that neuron I spikes, given that it is in a state xi. So what we do is we sample independently a uniform random variable ui in 0, 1. And so if it is below that threshold, we spike. And if not, we stay equal to xi. And so this is the first term of the first equation here. And in all the cases, cases, we aggregate the arrival process. We add mu ij. So mu ij is kind of given by it's the kind of the synaptic weights if you want. And we add it for each node that has fragmented. So for each node that where the uniform random variable is below the threshold, we add mu ij. And we define the dynamics by induction for all the discrete times. So what happens in the replica mean field dynamics? In replica mean field dynamics, you have an additional index n, which is the replica index. So we have m replicas. And in each of the replicas, you have k nodes. So y, m, and I is the state at time 1 of neuron I in replica n, given that there are m replicas. But the dynamics don't change that much. The only thing that changes is in the arrivals term. You basically take an additional sum over all the replicas, and you have this routing term, which basically means that you aggregate mu ij to your state only if node j in replica m has fragmented and the random routing chose replica n for the neighbor I of j. Sorry. Okay, so what you can see is that you have a sum of m terms, basically m minus 1 terms, and they are all kind of weight 1 over m because of the routing term. The last indicator is basically of order 1 over m in some sense. So now so this has been very abstract. Now I'll give some little kind of to explain the behavior of the system also has some drawings. So the base model is, I'll go over this pretty quite quick because we kind of have seen this one already, well, in continuous time. But the idea is that when a neuron spikes, it goes to 0. And whenever another neuron spikes, all its neighbors are incremented by the corresponding synaptic weight. So what happens in the replica mean field model? So now here, even though I put 3 little dots, there's a fixed number of replicas. There are m replicas. But what happens is, if, for instance, we'll focus on the spike on time 1, in replica 2, the neuron 4 spikes. And so for this spike, we say that we have a choice for its neighbor 1, we choose replica 1, and for its neighbor 3, we choose replica 5. Then we increment the neuron 1, 1 by mu 1, 4, and we increment neuron 5, 3 by mu 4, well, mu 5, 4. But so what happens when the number of replicas goes to infinity? Now we can sort of look at one replica, and what happens is that all the neurons become independent. All of the dynamics now only we can replace the arrivals process by a Poisson random variable here because we're in discrete time. And so the state of a neuron only depends on itself. But why, what's the kind of the point of this is that the parameter of the Poisson process will depend on the geometry of the initial network. And this is what I'll talk about at the end. So what happens intuitively is that we have the arrivals to a given node. You can see it's a sum of rare events because of their order 1 over m. And so they should converge in distribution to some kind of Poisson law. And since the probability that two nodes in two given replicas interact is in 1 over m as well, you should have some kind of asymptotic independence between replicas. Because what would happen is that because of the mixing, you basically never receive, in the limit, twice a spike from the same source. So because of that, your arrivals become very uniform, and because of that, you get some kind of asymptotic independence between replicas and between neurons. And so the goal is to prove this intuition. I won't go into much detail about that because I'm not sure it's very interesting to many of the audience. You can look at the article if you're interested in that. But the idea is to sort of propagate and to show that the replica mean field dynamics propagate a form of asymptotic independence in time. So we introduced this condition of pairwise asymptotic independence, which is basically what we want the initial conditions to verify. We want them to have a product form for the MGFs, for the moment generating functions, when the number of replicas goes to infinity. And what we say, this is what the main result states, is that if the initial conditions verify this hypothesis of pairwise asymptotic independence, then the replica mean field dynamics will propagate this hypothesis, and that you will still have pairwise asymptotic independence at time 1 between replicas and between nodes. And moreover, the arrivals to a given node will convert in distribution to a compound Poisson distributed random variable. So a compound Poisson distribution is just a Poisson number of IID random variables. So just a slight generalization from Poisson. And so if you look at the results for discrete Galvez-Schwarz neural networks, what you have is that you can have an explicit formula for the MGF of the arrivals to a given node. And what you get is that you, at the cost of introducing the mean firing rate, because theta I is the mean firing rate of neuron I, you get an explicit formula for the MGF, and you can see that it depends on theta I and the mu ij's. So the arrival process becomes all the new nodes become independent, so you still have k nodes, and but the arrivals become Poissonian, and you have a dependence on the spatial structure of your network. And in the fully connected case, you just get a Poisson random variable, so it's even simpler. And as naturally, you don't have any more dependence on the structure of the network since it's just fully connected. And so, as I just mentioned, I think I'm probably out of time. I started a bit late, so I think I'm fine. As you can sort of, I presented it here in the case of Galvez-Schwarz discrete dynamics, but you can generalize it to a whole lot of different discrete time dynamics, not necessarily neuron related. But even in the neuron case, you can add many things like randomized interactions. You can make the dynamic depend on time, so you can sort of kind of model some learning dynamics, even though I haven't necessarily looked into that much. You can add some exogenous Poisson input if you want. But there are still quite a few open questions about the replica mean fields. So in particular, the continuous time result is probably true, but there are still some small holes in the proof. And another open question is to include inhibitory behavior, because I haven't really spoken about the proof, but it relies on some conditioning and some of the MGFs, and the techniques don't really generalize to, for instance, characteristic functions. So you cannot really go away from having n valued random variables. You cannot really go to to Z, for instance. So it's not easy to include inhibition in the base discrete time model. Okay, so I think I'll stop here, and I'll be happy to answer any questions if you have them.
Thank you for your talk. So, are there any questions in the audience? Patricia. Okay. Let's start with you and then.
Okay. Thank you for your talk. I have a kind of, I know that you haven't proved it yet, but since you know very well how it works, do you have an intuition of why the replica mean field is close to the original model? What are the parameters that are making them close?
So, okay, there are maybe a few ways to answer your question. One is that, as I said, since you have what you do is you replace the interaction term instead of replacing it as in the traditional mean field by an expectancy of the point itself, you replace it with a Poisson term, and so that when the parameter of the Poisson sort of has some relevance in terms of the spatial structure of the model. So you kind of have maybe in this way you have more information that you would have without. And another way to answer the question is to say that in the stationary case, so in the stationary case in continuous time, for instance, if you look at the stationary regime, what you do by making a Poisson approximation is kind of ignoring something called palm bias, which is kind of well known. So you kind of it's an approximation that's kind of I don't know how should I put it. It's an approximation that kind of you know what you lose, kind of. I don't know how I should put it in another way. Okay, so for any stationary framework, for any stationary point process, you can associate with it something called the palm version of it, which is kind of the same process but conditional on having a point in zero. And so making a Poisson approximation in the stationary regime is the same as ignoring palm bias. So assuming that like you assume that you don't have any bias on the fact that you have a point in zero. I don't know if that's clear.
Yeah. So we have plenty of questions. I have also one. I don't forget you, Wilhelm. We come back to you immediately. But
Thank you. Did some authors study this type of models with Replica for other types of model, not only neurons model?
Yeah, so the replica mean fields, as far as I know, originate in the 70s in Russia. So by the Dobrushin school in Moscow, they studied the replicas basically what they did is they studied randomized interactions between queuing networks. And so, but it's not really the same setting because there's no it's not really a network that you take copies of. It's more that you have a queue and you have queues and you randomize interactions between queues. So it's kind of a simpler setting in some sense. And then the seminal paper concerning the applications to neuroscience comes from François and Thibault. And there are a few people who studied replica mean fields of other things, but it's kind of a new subject. So they looked at for elephant random walk. They looked at the replica mean field limit for elephant random walk. That's it as far as I know.
Thank you. I think I understand a little better what happens in the replica method. So you have this very clever construction where you have the replicas, you propagate the spikes, and then, if I understood correctly, there is some information about the finite size network that you preserve and that you can look up from the limit. Now, can you engineer the way you propagate the spikes within and between the replicas so that you preserve particular information that you're interested in?
What kind of information are you talking about, concretely?
Well, you said that the replica, the mean field limit, had contained information about the original network, but not all the information. Am I correct?
Yeah.
Okay, so there's some information that's missing.
Yeah.
Okay, my question is, can you re-engineer the way you propagate the spikes so that another information you were more interested in would be preserved? Am I clear on the question?
Yeah, the question is clear. Thank you. I think that like the base answer would be no, except in maybe some particular situations, because the idea is that you don't really control what you lose. You know exactly what you keep. Like what you keep is what you lose is that you lose correlations between the neurons, and you kind of hope to preserve some element of the correlations inside the Poisson structure. But what you concretely have is you have the synaptic weights, and you have a memory sort of the synaptic weights. But I don't think you could hope to save something else than that. So, okay, I hope that's clear. I hope that answers your question.
Yeah, thank you. And then there is the question by Wilhelm. So if you want to unmute yourself and.
Yeah, thank you. It's related to the first question. So how can you measure the quantity? How can you assess the quality of approximation? So do people look, for example, at the covariance structure of the process, or autocovariant function, something like this?
So this is actually maybe more a question for Lu Yan, who could probably just before me, who looked at things like that. So I don't know exactly. I know that Thibault and Lu Yan have some simulations of and that show that replica mean field seem to better approximate in certain regimes the initial dynamics so better approximate them than the thermodynamic limit. But as to how it's done technically, since I haven't really looked into that, so I'm not sure I can answer your question myself.
Okay, thank you. But once again, so what is it? So you are replacing. You look at you are looking at copies of the independent of the original network. You substitute with the Poissonian input. What is the benefit of that? Is it a complexity reduction? What is the precise complexity reduction there?
So the complexity reduction is that as the limit, you have k independent processes. So you have k nodes at the beginning, having a finite network, and at the end you have still a finite network, but you sort of assume that you replace them by independent versions of themselves by replacing the interactions with Poisson process. So the reduction in complexity is that you lose this correlation structure, and you replace it with something that kind of have some kind of memory of the correlation of the original correlation structure.
But the Poisson input must come from the approximation, right?
Well, so the way to see the way I think the right way to see it is that the replica mean field construction is a way to construct a physical system that is constructed based on the original model, and which converges to this limit model with the Poisson approximation. And so what you do basically is that instead of looking at the limit you obtain by the traditional thermodynamic limit, you look at the limit, the approximation given by the limit replica mean field model. And so you lose, as in the traditional replica mean field, you lose some things.
Sure, yes.
You just lose different things.
Okay, thank you.
Thank you very much. So if there are no other questions in the audience and on YouTube or Zoom, then let's thank all the speakers of this morning session.